In the last video, we started applying the polarity of bonds to polarity of molecules. Just as a reminder, we learned that if there are only nonpolar bonds in a molecule, then overall the molecule is going to be nonpolar. We also learned that if the molecule is small, so like only one or maybe two central atoms, and there's one and only one bond, or one and only one polar bond, pardon me, then the molecule is going to be overall polar. We learned that with both of those cases, the shape, so whether something is, linear, tetrahedral, whatever, it doesn't really matter in either case. But that might be asked, that leads to the question, what if there's more than one polar bond? So if there is more than one polar bond, then we do need to look at the shape. So that's, when I say shape, I mean the molecular geometry. We need to think in 3 dimensions, and we need to apply Vesper theory, which I don't know if I mentioned it before, but that stands for valence shell electron pair repulsion theory. So if there is more than one polar bond, then we have to see if those individual polar bonds cancel each other out, or if they don't cancel. So if the individual polar bonds in a molecule cancel each other out, then overall the molecule will be non-polar. So let's look at an example of this. Let's do carbon dioxide. Okay, so carbon dioxide. Here we have a molecule where there are definitely 2 polar bonds, right? Like there's a carbon and oxygen bond there and a carbon and oxygen bond there. So the oxygen is much more electronegative than carbon, and it's going to pull the electrons in that bond toward it, which will leave a partial negative charge on the oxygens and a partial positive charge on the carbons. Now, what we are going to do is still recognize that these partial charges are here, but I'm going to erase them because I think it's easier to think of it in terms of arrows. And so if we're thinking about like a blanket being shared among all of these atoms, the oxygen is pulling the blanket, so this oxygen on the right is pulling the blanket towards itself. The oxygen on the left is pulling the blanket towards itself. But overall, we're still getting that the blanket isn't moving. And so when we say that the blanket isn't moving, what that's kind of telling us is that the dipoles are canceling each other out. So, and you can see how this happens because they're in exactly opposite directions. The dipoles cancel. So I'm going to write the dipoles cancel, and then in parentheses, just a way of thinking about it. It's not actually a blanket and nothing is actually moving, but a way of thinking about it to help kind of, just mental gymnastics to get to the answer, is that the blanket isn't moving. So blanket doesn't move. So now I'm going to go back to putting those partial charges in. So if that whole blanket moving or not moving thing doesn't work for you, then maybe this will. So we're putting in the partial charges, and whoops, that's a partial negative, not a partial positive. And what we're going to do is we're going to look and see if overall the charges are balanced or unbalanced. Well, looking at it, it looks like you can see, okay, there are partial negative charges and a partial positive charge, but the partial negative charges are on opposite sides of each other. It's so overall it's balanced. So now let's look at what happens if we have individual polar bonds in a molecule that do not cancel. Well, first off, if they don't cancel, then they're going to reinforce each other, and overall our molecule will be polar. So overall molecule, yes, I spelled that right. Overall molecule polar. So an example of this is good old water. I love water. It's great. Okay, so I'm going to draw it a couple of different ways. The first way I'm going to draw it is in kind of a leading way to help us visualize and see why exactly this is polar. But I'll draw it in another way in just a second. Well, more than a second, in a bit. So with this, I have that my bond dipoles are pointing toward the oxygen, and I see that there's a partial positive on both of the hydrogens and a partial negative on the oxygen. Now, we have the same kind of thing happening here, like the same charge distribution as we have happening over here, right? Like well, not exactly the same, but the partial charge of the middle atom is different than the partial charges of the atoms on the fringe. So the reason that this molecule is polar is because overall it has a bent shape. So there's a bent shape, whereas here it's a linear shape. So whereas with the carbon dioxide, the linear shape made it so that the bond dipoles would cancel each other out. The bent shape of the water makes it so that the bond dipoles don't cancel each other out. So if you are thinking of like, or if you were using the blanket analogy that I introduced, it's kind of like you have a blanket that's being shared among all of the atoms in this molecule, and the oxygen is just like hogging it. It is pulling it away from the hydrogens and towards itself. So you can see that, like, since the blanket moves, since it's being pulled more toward one area than anywhere else, since the blanket is being shared unevenly, it's like the electrons being shared unevenly, and that means that overall the molecule is polar. So we'll say in here that the dipoles don't cancel. And so, in other words, in our analogy, the blanket moves. Again, there's not an actual blanket, and the blanket and the electrons aren't actually like moving. I mean, there's still a separation of charge with both of these examples, but it's a way to help us get to figuring out if something overall is polar or nonpolar. Now, I said that I wanted to draw this in a different way, so I drew the water in a way that showed how really clearly it was bent. If I drew it like this, that's an equally correct Lewis dot structure. When we put in our bond dipoles, however, we might be misled, because here, if we fail to think in 3 dimensions, we might think, oh, well, they're like pointing in the same, like they're both pointing toward the middle, so they cancel each other out. But it's because we have to think in 3 dimensions that that makes this molecule of water polar instead of nonpolar. So in other words, don't get tricked thinking a molecule is flat just because it looks flat. Always, always, always think in 3 dimensions. So I've summarized that down here by saying shape matters. So think in 3 dimensions. So that's it. That's the general chemistry way, so the way that or similar to the way that you learned in 121, to figure out if small molecules are overall polar or nonpolar. We first identify the bonds, seeing what bonds are polar and what bonds are nonpolar. Then we think of the shape, and then using those two together, we figure out if the bonds, well, we've done it, so I will move on. Okay, so let's go to an example. So, example, draw a picture to explain why CH2Cl2 is a polar molecule. Okay, and so I wanted to do this one together. And so first, I think the very first step with any of these is, if you're not given the Lewis structure, that's the first thing you need to do, is write out the Lewis structure. So rather than going through how to do that, I'm just going to show you what it is. But it would be a good idea for you to practice that if you're not totally confident on it yet. Okay, so I'm going to draw this a couple of different ways. So I have CH2Cl2 drawn like this, and I'm going to draw CH2Cl2 like this. So both of these pictures represent exactly the same molecule, and they mean exactly the same thing, which is why it's so important that we think in 3 dimensions. So what we are going to do is first determine whether there are any polar bonds. Well, okay, we have carbon-hydrogen bonds. We know those are non-polar. And we have carbon-chlorine bonds, and those are polar. So then we have to figure out which element is more electronegative. Is it carbon or is it chlorine? Well, we pull up our periodic tables and we see that chlorine is closer to fluorine than carbon is. So our bond dipoles are going to be pointing towards the chlorine. Okay, so pointing towards the chlorine. And I'm drawing this on both diagrams just so I can illustrate it. Okay, then what we need to do is think about it in 3 dimensions. So we think of this molecule as being tetrahedral. Okay, so I'm going to draw a picture that shows it in a way that is more, shows more clearly how it's tetrahedral. So I'm going to draw this, I'm going to use the wedges and dashes thing. Okay, so there's my wedge, there's my dash, and for good measure, I'll kind of do a little dotted thing to try and represent this tetrahedron. So remember, that's where the carbon is in the middle, and then all of the things that are connected to the carbon are pointing out to the edges of the tetrahedron. Okay, so the shape of this molecule is tetrahedral, and I'm going to draw the bond dipoles in here as well. So the shape being tetrahedral means that no matter where we put these chlorines, whether we have, one here and one here, or maybe we rotated it and one was like up here instead, there's no way that those chlorines will ever be pointing in exactly the opposite direction. So because they'll never be pointing in exactly the opposite direction, that means that our molecule overall is definitely going to be polar, because they're like the blanket is always being pulled pulled in one direction. So over here we have our blanket, the chlorine. This chlorine is right here. The chlorine connected to this carbon. It's pulling the blanket over towards it, and this chlorine is pulling. This one on the bottom is pulling the blanket towards it. So overall, we would see the blanket, instead of being evenly distributed among everything, it would be much more like over here. Okay, so it's not evenly distributed, and that means that the molecule is a polar molecule. So let's write that out. So the shape is tetrahedral. There are 2 polar bonds, and because the shape is tetrahedral, those 2 bond dipoles, those 2 polar bonds, will never, ever, ever cancel. So 2 polar bonds will never cancel. Now you might be saying, Allie, but look right here, I can see that we can draw it in a way that makes them cancel. And, well, remember, if you were thinking that, what I would encourage you to do is to remember to think in 3 dimensions, to remember that when we draw something on paper as flat, it is not always, oops, sorry, I sneezed. I'm glad I was able to pause before I got that. Okay, so we can't think that just because something is drawn as flat that means it's actually flat. So these pictures are a little bit misleading. We need to think in 3 dimensions. So think in 3 dimensions. So please stay tuned, because we will, in the next chapter, learn the shortcut organic chemistry way to evaluate whether a molecule is overall polar or nonpolar. But I don't want you to think that because, it's a shortcut, that means that you can forget about this way, because sometimes this way is the only way that's going to work, especially when we are dealing with small molecules. So let's get some practice with this. So I want you to go ahead and pause your video and try this out. Label each molecule as polar or nonpolar, and then explain why. Defend your choice. So you're going to go through the same procedure that we've done before, where first you figure out if there are any polar bonds, and then you figure out what the shape of the molecule is, and then you figure out if the polar bonds cancel each other out or reinforce each other. Okay, go ahead, pause the video, try it out. We'll go through it together. Give you the answers in 3, 2, 1. Here they are. So the first one, there is only one polar bond, and with this one we didn't even really need to look at the shape because we know that if the molecule is small and there's one and only one polar bond, then that molecule is going to be polar. There's an uneven electron distribution. So if we think of this as like, there's a blanket of electrons that are being shared, the oxygen is pulling the electrons towards itself, and the electrons aren't being shared evenly anymore. Okay, so this is polar. For B, this is an interesting one because we can absolutely have molecules where there are polar bonds, but overall the molecule is nonpolar. So there are 4 polar bonds, and you would think that, oh, well, with so many polar bonds, doesn't that mean it's automatically a polar molecule? And the answer is no, because they all cancel each other out. So even though each one of these chlorines is pulling the blanket towards itself and away from the carbon, since they're all pulling in opposite directions of each other, they end up canceling each other out, and we're getting an overall even electron distribution. Okay, that's it for this video. In the next one, we are going to apply the whole polar, non-polar thing, to one of the most important and recurring things that we're going to see throughout this entire course and that you're going to continue seeing in your biology courses, and further forward, and that is the concept of intermolecular forces. Okay, I'll see you then. Bye.